Let's now get more in depth about how to size CSTRs and PFRs. This example is long and it will include many concepts, so make sure that you're writing good notes about it. You will also have some review on numerical methods to solve integrals, and we'll be reviewing those quickly, and I will be referring you to more references in case that you need to review this in the future. So take the time to pause the video and copy this statement in your notes. We're going to be working the rest of the video with this data. I will not refer back to it. You should have it in your notes, or you can have a print screen or something like that so you can have it available later. Consider the isothermal gas phase isomerization of reactant A going to product B. This reaction is happening under constant pressure and constant temperature. With pure A entering at initial molar flow rate of 0.4 moles per second, and we are assuming that there are no secondary reactions happening in the reaction. When we make the experiments, we collect the rate of decomposition of A as a function of the conversion at the end of the reaction, or at the end of the reactor. So remember that for both the CSTR and the PFR, reactor volume varies directly with the molar flow and with the reciprocal of the rate of consumption of A. So it's easier just for me to show you this in Excel. You can easily do this by hand too. It's not that bad doing the calculations. However, this is just to speed up the process. I calculated the y-axis and then I graph it out, and I received and I produced, right, and I created the Levenspeil plot for the example. So I'm going to be working with this graph and this data, so you will see it being called, right, in different occasions on the upcoming examples. So now let's work with specifically the sizing of a CSTR. The first question that we have to do, or the first thing that we have to do, is to calculate the volume achieved to achieve 80% of conversion for this particular reaction, and they're asking us to do this from the data. Remember, you can do it from the data, or you can do it with the Levenspeil plot. Just for the sake of walking you through all these statements and making sure that you understand, we're just going to do it from the data. This is more algebraic, but at least you can see the comparisons between the two methods. Remember that for a CSTR, so when the rate at the exit condition is the same as the conditions inside the reactor, we know, right, that we are having a perfectly mixed system. So that's one of the assumptions for the CSTR. Therefore, from the data, we can obtain information of all the parameters, right? In this case, the reaction rate that we can use, right, in this design equation. Okay, given that the initial molar flow rate equals to 0.4 moles per second, we can substitute everything into this equation, and we can get that the volume of the reactor equals to 6.4 meters cubed, or which is the same thing as 6,400 decimeter cubed, or equals to liters. Okay, so these conversions are very, very important, and they are very common in reactor design classes. Okay, so let's move on with the Levenspeil plots. Now we want to shade the area in the figure, right, on the Levenspiel plot, and we are asked to calculate the volume necessary to achieve 80% of conversion. So I already explained you how to get the graph. So once we have the graph, we can notice, right, that I'm gonna change color here, orange, because we're gators. That if I go here to 80% and then I go here to 8, right, on the y-axis, from the equation, right, the design equation from the CSR, we notice that we have that the y-axis in this particular graph corresponds to the height of this rectangle, and this conversion number, right, magnitude, correspond to the base of this rectangle. So that means if we want to shade it, right, what correspond, the volume, it will be the area, right? So you can do the substitution again. You know that this value from the graph equals to, I'm going to change color back again, equals to 8 meters cubed times 0.8 equals to 6.4 meters cubed. Okay, so it doesn't matter what information we have, we should get to the same result. It will depend on the available information. This procedure shows how powerful is the Levenspiel plots if we have them available, and how easy it is to calculate the volume just by understanding what is the meaning, right, of the area of that rectangle. So I recommend you to pause the video right now and write down the statements. Okay, if you're back with me, before we start straightforward solving what they're asking, I really want you to think about what is the statement, right? And for example, now we're talking about a PFR, which means that the design equation is different from the CSTR. The conditions as the inlet flow and the data is the same. The first part of the statement asks you to use integration solution to determine the PFR volume to achieve 80% of conversion. If we solved some problems where we had the Ray law equation, and with the Ray law equation we can get the analytical solution of the first order integral. However, we don't have that. So that means that if we have data, we need to use numerical methods like Simpson rule. If you don't remember that, we're going to review it, to actually get the area under the curve. Remember that for PFR, the Levenspiel, the volume corresponds to the area under the Levenspiel plot. The second part is shade the area in the plot. We just mentioned that, so we're going to get through that with the graph. And then the part C make a qualitative sketch of the conversion of X and the rate of reaction. Here, they just want us to kind of imagine, right, the length of the reactor volume, and then see what is going to be the profile of rate of decomposition, and another graph with the profile of conversion with changes in volume. This means that because we don't have, we know how to calculate the area under the curve, right, for 80% conversion. We need to do that for every one of the volumes that we have available based on some numerical methods again. So this problem is kind of long, but it's because it involves a little bit of algebra and things that you're going to be reviewing, and I'm going to take the time to help you to understand it. To get the numerical solution for the volume at 0.8 conversion, we need to start, as always, with the mole balance and then solve for the volume using limits, right, or integral conditions of 0 and volume 0, and 0.8 is the volume that we want. We notice that from the statement, we don't have an expression of the rate law decomposition of A, or the rate law. Therefore, the only way to do this is with the provided data. So when you have data and you have an integral, you need to use numerical methods. So some numerical methods that will be discussed or will be used in this class includes the sinusoidal rule, the Simpson 1/3 rule, the Simpson 3/8 rule, and 5-point quadrature formula. There's also other formulas depending if we have more than 5 points that we can use. So the numbers here on the right, are the total number of data sets that you can use for that specific rule or method that we select. The way we select the method is first with the available data and how many data sets we can divide, right, in the corresponding spaces between points. Okay, so it will really depend. These are the most commons in the class because if I'm gonna ask you to solve this in an exam or in a homework, it has to be doable, right? It has to be possible to make and something that you can make on paper. And these are the simplest one because of the total number of available data sets. For our example, we're gonna be using the 5 points quadrature formula. And the reason is because we can define from the data 4 equal segments between x equals 0, the conversion equals to 0, and the conversion equals to 0.8. That segment, right, can be calculated by just subtracting the final x, which is 0.8, I'm sorry, minus the initial one, which is 0, over 4, because we want to space all of them in 4 segments. Okay, that equals to 0.2. So that means that every 0.2, right, in the x-axis, we're gonna select the data set. So that means that we're gonna use the data set for x equals to 0, x equals to 0.2, 0.4, 0.6, and 0.8. And these values, right, for the y values for the formula will be used on the in this numerical method. So now we can substitute the numbers from the data set in the 5-point quadrature formula. We get to this expression. Okay, this comes from the definition of the method that we selected. If we substitute the values obtained from the table, right? These are the values from the process data. We obtain the volume of the reactor using numerical methods. Look that the volume still similar, right, to the one, well, we haven't done it. This is the first time. This is the PFR, so this is the volume for the PFR reactor. Now we're going to do part B, which is the other way of doing this problem. But before that, let's imagine, here we have our friend that she's really happy. Let's imagine that you have available PFRs that are 0.1 meter in diameter and with a length of 2.8 meters. How many PFRs you will need and how will you arrange them? Remember that we are basing pretty much this statement on the obtained value here of the volume. So using that value as a total volume needed, let me know and we will discuss this on next class. Make sure that you study this and you have an idea how to solve it. Okay, so for this part C, they ask us to sketch the profile of the rate of consumption of A and the conversion down the length of the reactor. So that means that they're asking us of two graphs. So we're going to focus our attention to collect this data in terms of conversion. But if you get the volume for that conversion, you already have the rate of reaction on the data set. So what we're going to do is that we're going to focus on that. So we're going to create here a data table that we're going to be filling out, right, and use it later for our profile. So remember, we're trying to solve numerically the volume for each of the conversions. So we have to look at what we already have. We already have from the previous example that at 0.8, the volume in liters, right, equals to 165. And the volume at the beginning equals to 0. So we're trying to get these three points. So what we can do, right, is to use the numerical method. So from the original data table, we have data for 0, 0.1, and 0.0. If you look at that table, you're going to see that. So because we're trying to get the area, right, under the curve all the way to 0.0, it is more appropriate, right, to get the Simpson rule of thirds, because we can divide, right, from 0 to 0.1 to 0.1 to 0.2. We can divide two equal space segments that provide us 3 data points. And with that, the rule can be used. So I'm going to put the values here and try to solve it. So expressing, right, the rule of thirds and substituting the values, we get that the volume for this conversion equals to 118 liters. Take the time to work out the math. Focus on working to get the volume when the conversion equals to 0.4. If you look at the data set, you notice that you have data sets that allows you also to divide equal segments, in this case 2 segments of 0.2. So with that, that provides us, right, or allow us the opportunity to use again the Simpson rule of thirds. So in this case, I'm just going to put the solution for this. So remember, you have to calculate what is age, right? So you can use it back into the equation. If you do the same thing, right, based on the data set of the original table that I gave you at the beginning of the video, you get that the volume equals to 551 liters. So that equals to 551 liter. So we're still missing one data point. So let's focus on get that one. So now for the volume at 0.6 conversion, we notice that from that original data set, we can get 3 equally spaced segments of 0.2. So if you look at it, that gives us 4 data points that we can use, including x equals 0 for this data set. So once again, I'm going to just write the rule, the Simpson rule of third eighths, which is the one that fits the number of data points that we have, and then I'm going to allow you to solve the problem. Substituting the values into the Simpson's rule of third eighth, which is this equation that you have here, you get a volume of 1093 liters. So that will be the final point needed for the conversion profile. So what I'm going to do now is switch to my computer so you can see the different profiles that you get for this example, boss. Okay, so if you look closer to the following graphs, you can see the characteristic plot for isothermal reactor, for a PFR. Here you see as predicted, right, as we are moving through the length of the volume, the profile for the reaction rate start decreasing, right? We see that, remember that the flow, the reactants are being consumed, and we are trying to define the volume to get that 0.8 conversion. And you can see that more clear here in this graph with conversion, where you basically see that you start that at a volume 0, there's no conversion of the reactant. As the reaction progresses right through the volume of the reactor, then we see that reactant A being consumed. So collecting information and comparing, we see that for a conversion of 0.8, the volume of the CSTR and PFR that we calculated previously, we can see as predicted as with the Levenspiel plots. We concluded, right, that the volume of the CSTR and PF is larger than the PFR under the same conditions. So this applies for isothermal conditions and reaction order larger than 0. The reason why this happens is that, remember that for the CSTR, the conditions inside the tank are equal to the ones outside, exiting from the tank, which means that the reactor is constantly operating at lowest reaction rate. However, as compared to the PFR, the reaction, the conversion start very low and start increasing, or the reaction rate, right, start at very high at the beginning of the volume, and it starts decreasing along the volume length. This profile, these trends are typically true under these isothermal conditions. However, there are some exceptions, such as autocatalytic reactions, product inhibited reactions, and non-isothermal exothermic reactions.